morning, everybody.
Good morning, sir.
Is it the same strength in the previous class?
No, sir.
Was
23 members attended, sir.
okay? They are finding any difficulty in login, or they are doing deliberately?
Maybe network problem, sir. It's cloudy, no, sir, weather.
Yeah, yeah. Okay, okay. No problem. Shall I start the class, or we should wait?
Start, sir. They will join.
Okay, yeah. We'll start the class. So today we
Okay,
will
sir.
see two film. Thank you. Yeah. Today we will see about the two film theory or two resistance theory. Okay, it is also known as two resistance or two film theory. Already we have seen what is film theory. Film theory is nothing but a single film. He has derived the other Whitman has derived the uh, for the single film theory. He has derived the flux equation. We will apply that theory to the two film. Okay, in which the first film is the bulk gas film and second one is the liquid film. We already given I already given one example for this one. NH3 is being transferred from the gas phase to the liquid water. Okay, we already shown the video. Yeah, from the same video, I have taken this picture. As you can see that the transfer of NH3 from this bulk of gas phase to the bulk of this liquid phase, there are two types of resistance or the two types of films are there in order to offer the resistance of transfer of NH3 to this water, liquid water. Okay, so the first resistance among is the gas bond. Gas film. Okay, we are indicating this with a ZG. ZG means the length of the gas film or the distance of the gas film, ZG, and distance or the length of the liquid film. This is so resistance 1 is the gas film resistance and resistance 2 is the liquid film resistance. Same when you see the concentration profile. If you consider NH3 is present here in the bulk concentration and it is getting transferred towards the liquid phase, then the concentration profile of this transformation will looks like this one. See, first, for example, the gas phase, we usually indicate the concentration of any component in the gas phase in according to their partial pressures or the pressures. Okay, in terms of pressures only, we will tell what is the concentration of that particular gas. So in the this is overall a gas phase, this one, and this is the interface which separate the gas phase and liquid phase. Okay, from the in the liquid region, there is according to film theory there will be one film will be formed. Okay, whose thickness in the single film theory is indicated as delta. Here for the convenience we are indicating the thickness of this liquid film as ZL. Okay, which is the distance of liquid film. Okay, then the thickness of the gas film in the gas phase side is ZG, which is the thickness or the length of the gas film, this one. So according to film theory, what he is saying, whenever there is two phases or interacting with each other, there is a formation of one film on the both sides, both faces side. There will be one formation of film. Through this film only the mass transfer will take place. According to that Whitman film theory is, whenever there are phases interacting with each other, each phase will form their respective film. Then only through that film only the concentration difference will happen. Therefore, this due to this driving force only the mass transfer will take place. Apart, you can see, apart from this film, no concentration gradient is there. Everywhere the concentration is linear. See a straight line. See, this is CA straight line. Concentration of A in liquid phase is straight line here after the film, after this film thickness ZL. Okay, here also see in the gas phase the concentration of the component A in the gas phase is throughout is uniform. PA, it is not at all changing. The graph is straight line here. After the film only, the concentration of A is dropping. Okay, similarly, the concentration at interface in the liquid phase is just dropping up to the film only. Okay, after the film, it is remaining as the same as that of bulk concentration. Okay, only the mass transfer takes place within this film only. According to film theory, mass transfer will take place within the film. Now, what are these parameters? What are these notation schemes? So, PA is the partial pressure of A in the gas phase. PA is the partial pressure of component A in the gas phase, whereas Ca star is the equilibrium concentration of component A, which is in equilibrium with PA. Okay, so the relationship between PA and Ca is given by Henry's law. Okay, Henry's law. What the Henry's law is saying that whenever the dilute solutions are there, the concentration can also be expressed in terms of its equilibrium partial pressures, or whenever the concentrations are there, we can express the equilibrium equilibrium concentration in gas phase as its partial pressure. Now, from the Henry's law, what we can say, PA is directly proportional to Ca star. Okay, whereas the proportionality constant in between them is H, capital H, which is Henry's law constant. Henry's law constant depends on the particular experiment, or depends on particular gas and liquid. The value of H will depend. So what he is saying, Henry's law, for the dilute solutions of gas being transferred into the liquid, partial pressure, whenever the concentration in the gas phase is expressed with partial pressure, its equilibrium concentration in liquid phase can also be expressed in its equilibrium concentration. So PA is directly proportional to Ca. The Henry's law is saying that PA is directly proportional to Ca star. So the proportionality constant in between them is capital H. So Henry's law overall is PA is equal to H into Ca star. Okay, similarly for the interface here, you can see these are two in equilibrium. Concentration in the liquid phase and partial pressure in the vapor phase or the gas phase is in equilibrium. So according to Henry's law, we can define the relationship between these two. Then from the Henry's law, we can define the relationship in such a way that PAI is equal to H into CAI, because these two are equilibrium at the interface. So PAI is equal to H into CAI. Similarly here, PA is equal to H into Ca star and PAI is equal to H into CAI. Similarly, in the bulk of the liquid phase, we can define the relationship between PA star and Ca. So same as the Henry's law. Henry's law says that PA star is equal to H into Ca. Whereas here you see PA is equal to H into Ca star. Here PA star is equal to H into Ca. Okay, these are the Henry's law which are defining for the dilute solutions of gases in the liquid. Okay, so for the dilute solutions only Henry's law will applicable. Okay, then this is the liquid film. This is overall liquid phase. Up to the interface, everything is the liquid phase. Up to the interface, from the starting of the region is gas phase. If you consider the this is overall Z. Okay, mass transfer region. This is so in the Z direction. So origin. This is if you consider since the mass transfer is taking place from bulk of the gas phase to the liquid. So liquid gas to liquid transformation is happening here. So we will take the gas film as the origin 0. Here Z is equal to 0. Whereas here you can see this is Z is equal to some Z. Okay, this is yeah, Z is equal to some Z. This is not a double-headed arrow. So this is starting from here to here. Yeah, so starting origin is 0. Origin is 0, or go we can say. So the ending point is Z, this one. So Z is equal to Z. The concentrations will be this one, uniform concentration Ca. When Z is equal to 0, the concentrations are throughout here is up to here, starting from here to here is Pa and Ca star. When Z is equal to 0, starting from here to here, all is the concentration of bulk concentration Ca and equilibrium concentration in Pa star. Within the film only the mass transfer is taking place, so it will vary. So now we have to do the mass. We have to perform a mass balance, or nothing but we have to do apply here the fixed first law of diffusion here, because already from the film theory we know that Na is equal to Ja. So Na is equal to Ja, where Ja is from fixed law of fixed first law of diffusion. So I already recorded the screen because of this is not working. I will share that one with you. Yeah, can you able to screen the live board on the screen?
Yes, sir.
VLC, including VLC. Yeah, I have recorded this already, the derivation, because live board is not working during the session. So just watch this, and if you have any doubt, just stop me anywhere and then ask me the doubt. I'm just playing whether confirm if you are receiving audio or not.
Yeah, for the overall process, overall gas to liquid transformation process, we are writing the equations. So, for the flux equation, we know from the film theory, Na is equal to Ja we can take. Then from the fixed first law of diffusion, Ja is minus dAb dou Ca by dou Z is the Ja. Now we have to integrate this one. We will bring dou Z on this side and integrate minus dAb into dou Ca. See here the boundary conditions are when Z is equal to 0, the concentration from starting of the process to ending of the process, when Z is equal to 0, the concentration is Ca star, as you can see from.
Yeah, you can see from this here, the concentration boundary conditions are defined here. See, when Z is equal to 0, so the concentrations are Ca star. Okay, in terms of liquid concentrations, we can express. So this is Ca star. When Z is equal to first we have to define the boundary conditions, then only we can fix the limit. So Z is equal to 0, the concentrations are Ca star. When Z is equal to some Z, the concentration is Ca. Similarly, for the gas phase, we can define when Z is equal to 0, the partial pressure is Pa. Okay, similarly, when Z is equal to some Z, the partial pressure is Pa star. So when Z is varying between 0 to Z, the limits are when Z limits are 0 to Z, we can say the concentration limits are Ca star to Ca. When Z is varying between 0 limits or Z limits are 0 to Z, we can define in from Pa to Pa star. Okay, that's the limitations. That's the limit we have to fix. Okay, just watch the video.
The left side of the graph, two film graph, and when Z is equal to some Z, capital Z, then the concentration is varying as Ca. You can see from the right side of the graph. So now we have to integrate this equation. You can cancel out integration and derivative. Then what happens? Upper limit minus lower limit, we have substituted NAZ, and here the minus DAB is there, and upper limit minus lower limit we can substitute. Upper limit is Ca and lower limit is Cs star. So now what we can do, we can send this DAB by Z. We are sending this minus to that side. So multiplying with this variable, so we can interchange the variable Cs star minus CAB. So now we already know from the mass transfer coefficient Mass transfer is nothing but flux is directly proportional to concentration driving force or the pressure driving force. And the left out term, whatever will be there, will be the mass transfer coefficient. Since we are writing this for overall process of mass transfer, so we are taking this is overall mass transfer coefficient. Now we can define this as Na is equal to KOL CA star minus CA. Okay, this you can consider from equation 1. Okay, equation 1 we can consider equation 1. And what happens when we write in terms of gas terminology? Now we have derived the liquid phase. Okay, for the liquid phase concentration in the overall process. But we consider in the gas phase, then we can write same formula. Na is equal to Ja. In case of Ja, we are writing minus dAb dou Ca by dou Z. We already know for the gases Ca is equal to Pa by RT. So we can write, we can substitute in that formula, Na is equal to minus dAb dou Pa by RT by dou Z. Now we can take RT, which is not a variable, which are constant, though we can take it out. So dAb by RT dou Pa by dou Z. Now we will just transfer the variable from other side, dou Z minus dAb by RT dou Pa. Now we already know from the graph, the two resistance graph, when Z is equal to 0, our concentration is Pa. When Z is equal to some Z, then our concentration is varying up to Pa star. Now integral derivative cancel, integral derivative cancel. Now we can say, we already substituted, I am writing the direct steps here. NaZ is equal to minus dAb by RT. So upper limit minus lower limit, we can substitute Pa star minus Pa. Then the left out term, NaZ is equal to dAb by RT. So we are just transferring this minus to inside so that we can interchange the variables Pa minus Pa star. Now this is this Z also we can send here, Z can cancel out from here. Now this is KOG, overall gas phase mass transfer coefficient. So we can write Na is equal to KOG into Pa minus Pa star. Okay, yeah, this we can consider equation 2. Okay, now what we can do for the individual film, for the individual gas phase, we can write the equation. So for the individual gas phase, when we write this equation, we already know from the gas phase, this is the equation. Na is equal to KOG Pa minus Pa star. So same equation we can apply for the individual gas phase. This is nothing but individual mass transfer coefficient Kg into whatever the concentrations varying from the higher concentration region to the lower concentration region. Since this is for only gas phase, so we can write up to PAI, interface concentrations. Now similarly for the liquid phase, we can write,
yeah, for the individual, I'm showing this one here in the PPT. Yeah, for the individual field transfer coefficients, we can write up to this region, only for the gas phase, this region, and up to this region for the liquid phase. Okay, now the concentrations, new concentrations for this region will be Pa to PAI, and for this region will be CAI to CA. Okay, that's what for the individual. Overall mass transfer coefficient meaning when we are taking the concentration from PA to PA star, we can write KOG. When we are taking concentrations from CA star to CA, we can write KOL. Whereas Kg, which is individual mass transfer coefficient, when we are taking concentration pressures from PA to PAI, we can write Kg. Okay, when we are taking the concentration from CAI to CA, we can take KL. That is individual liquid phase mass transfer coefficient, and Kg means individual gas phase mass transfer coefficient. See here from this equation, we already derived this equation now only. So flux is equal to overall mass transfer coefficient. This is gas phase overall mass transfer coefficient. Now the concentration, the pressures are varying overall. So PA to PA star it is varying. So this is overall mass transfer coefficient, gas phase mass transfer coefficient. Now this is the flux equation for liquid phase. So this is overall liquid phase mass transfer coefficient, KOL. Now the concentration you see it is varying overall CA star to CA. Okay, this is then individual. These are individual mass transfer coefficients. So flux is same equations we can write, but up to the single layer. This is for gas layer. This is for liquid layer. So you can see this is Kg is individual mass transfer coefficient. Now the concentrations, pressures are varying from PA to only PAI. Up to this region only it is varying. Similarly for the liquid phase, the concentrations are varying up to this region only, CAI to CA. Okay, this is individual liquid phase mass transfer coefficient. This is overall liquid phase mass transfer coefficient. This is overall gas phase mass transfer coefficient. This is individual gas phase mass transfer coefficient. Hope this there is a clear distinction between these two equations. Okay, overall is when we are taking concentrations from the start of the mass transfer to the end of the mass transfer. Individual means we are taking up to the interface only, up to the gas interface for the gas concentrations, up to the liquid interface for the liquid phase concentrations. Hope you understood that one. So same the derivation, and once again repeating that one. Yeah. Now from here you can watch.
Consider this as equation 3, and for the liquid phase we can write Na is equal to Kl into, already we have here, into Ca star to Ca, it is varying, so we can write Cai minus Ca. So we can write Cai minus Ca. This is equation 4. So from equation 3 we can write 1 by small kg is equal to, from this one, 1 by kg is equal to Pa minus Pai by N. And this is equation 5, you can say. From equation 4, we can write 1 by Kl is equal to this equation, Cai minus Ca by N. This is equation 6 we can write. Now see, from equation 1, and what is this equation 1? From equation 1 we can write 1 by KOL is equal to, so I am writing here directly, so 1 by KOL is equal to Ca star minus Ca by N. Okay, 1 by KOL is equal to 1 by KOL is equal to Ca star minus Ca by N. To this equation, what we can do, interface concentration we can just add and subtract Cai. Okay, now see Ca star minus Cai, here we can write this in this form, 1 by KOL is equal to Ca star minus CAI by Na. We can divide that into two summation of variables. So the left out, we have taken this, and left out is Ca, this we have taken. So CAI minus Ca is CAI minus Ca is the left out term. From our previous equation, Ca star minus CAI by Na is nothing but, from which equation? So the individual mass transfer coefficient equations. So this is individual. So here you can see CAI minus Ca by Na is 1 by KL. Okay, this is Ca 1 by, this is 1 by KL from equation 6. Okay, not this one. Okay, now we can write this as 1 by KYL is equal to, now Ca star is HPA minus HPAI by Na we can write, plus the left out term is 1 by KL. So this is, now we can take H common, 1 by KOL is equal to H common we can take, so PA minus PAI, PA minus PAI by Na plus 1 by K. Now this equation, whatever this variable is there, PA minus PAI by Na, so PA minus PAI by Na is equal to 1 by kg from equation 5. It is 1 by kg. So we can plus 1 by kg. So this is the relationship between overall mass transfer coefficient in liquid phase to the individual mass transfer coefficients in the both the phases. Similarly, from equation 2, you can write from equation 2. Then what is this equation 2? Equation 2 is this one. Na is equal to KOG. So we can write this equation as 1 by KOG is equal to PA minus PA star by Na. Same equation we have to write there and reduce the parameters. 1 by KOG is equal to PA minus PA star by Na. To this equation, same operation, plus PAI minus PAI we have to do interface concentration, load summation and subtraction of interface concentration. Now we have to write the variables like 1 by KOG is equal to now PA minus PAI by Na. We have to divide this overall variable into two different variables. This PA and this minus PAI we have used. Then left out is PAI minus PA star by Na. So by Na is nothing but 1 by kg. 1 by kg. This is 1 by kg. 1 by kg. Now we can write this one. So this is 1 by KOG is equal to 1 by kg individual gases mass transfer coefficient plus in place of PAI we can write the equilibrium concentration of H into, in terms of Henry star, H into Ci minus In place of CA star, we can write H into CA. We can write HCA by N. Now we can take because H common. So 1 by KOG is equal to 1 by kg. H we can take common. CAI minus CA by NA. So HCA. CAI minus CA is from equation 6, I guess. This one, CAI minus CA by NA is nothing but 1 by KL. So this is 1 by KL. This is. So now we can write 1 by KOG is equal to 1 by kg by plus 1 by plus H by KL. So this is overall gas phase mass transfer coefficient. This is individual gas phase mass transfer coefficient. Okay, this is overall mass transfer coefficient. This is individual gas phase mass transfer coefficient. This is individual liquid phase mass transfer coefficient. So these are the coefficients.
Yeah, I hope you understood this one.
Yes, sir.
Yeah, okay. From the boys side, anybody? Shall I have to explain once again? Just confirm me. This is very important derivation.
Explain once again, sir.
Okay, I think if my live board works, then I will now only I will derive. Otherwise, same video I have to play once again. I am putting off my video. Okay. See, I think concentrations terminology are okay. From the individual film theory we already written. So from the film theory, we can say Na is equal to Ja. We can say. Now what is Ja? From the Ja is nothing but fixed first law of diffusion. Flux from the fixed first law of diffusion. Na is equal to minus dAb dou Ca by dou Z. This is fixed first law of diffusion. Now this fixed first law of diffusion, now we have to integrate this one. So variables we are separating. Na from that side we are bringing dou z to this side is equal to minus dab dou ca is there. So dou ca. Now we have to fix limits. So in fixing limits, I already explained when z is equal to 0, the concentration is when this one z is equal to 0, the concentration is Ca star. When z is equal to z, the concentration is Ca. The same limits we have to apply here also. See, when z is equal to 0, the concentration is Ca star. This is okay. When z is equal to some z, the concentration is Ca. So like this we have to apply the limits. Now derivative and integral we can cancel out. Here also derivative and integral we can cancel out because this is a simple derivative. So now so Na integral derivative already cancelled out, upper limit minus lower limit, which is z minus 0. We can write direct z is equal to minus dab dou ca, derivative and integral already cancelled out. So left out term is upper limit minus lower limit. So upper limit is ca, lower limit is ca star. So ca minus ca star we can write. So then in order here minus is there. So this minus we can multiply within the bracket. So we can obtain Na is equal to dab by z. We are sending to the RHS side that one z. So dab by z into Ca. So because of minus we are interchanging the variables Ca star minus Ca. So this we are considering here you see from the definition of mass transfer coefficient. Mass transfer coefficient is nothing but relationship between the flux and concentration driving force. Okay, the flux is there, concentration driving force is there. So the left out term is only the circled one. So dab by z, which is known as KOL, because the concentrations here we are writing for the concentration overall system. For the two-phase system also we are writing the concentration balance. So we have to write this as a KOL, which is mass transfer coefficient, overall mass transfer coefficient in the overall system. So then similarly for the gas phase, when we are writing the fixed first law of diffusion for the gas phase, we have to say Na is equal to Ja. So Ja is equal to minus dab minus dab dou Ca by dou Z. Okay, then for the gases we already know Ca is equal to concentration is expressed in ideal gas law Pa by RT. So this Pa by RT we need to substitute here this one. So when we substitute, so this is Na is equal to minus dab dou. So in place of yeah. In place of Ca we have to substitute Pa by RT. So the left out is dou by dou Z. Now RT, this R and T are both are constants. They are not variables. We can take it out from the derivative term. So Na is equal to minus dab by RT. Since we are taking out RT by RT dou Pa by dou Z. This is. So now same integration we have to perform. Na dou Z we are bringing to the LHS side. Dou Z is equal to minus DAB by RT. Dou PA is the left out term in the RHS side. So integral between limits. So between limits, how can we fix the limits for the gas phase? See, when Z is equal to 0, the partial pressure is PA. When Z is equal to some Z, the partial pressure is PA star. So these are the limits. So when Z is equal to 0, the partial pressure is PA, and when Z is equal to some Z, the partial pressure is PA star. PA star. Now this is also simple integral. So integral derivative cancel and integral derivative we can cancel out. Now we can substitute directly upper limit minus lower limit here, upper limit minus lower limit here. So here you can see Na into upper limit minus lower limit. Yeah. Now upper limit minus lower limit we have applied. Na into Z is equal to minus DAB by RT is there, minus DAB by RT is there. This is DAB minus DAB by RT is there. Then upper limit is PA star minus PA. Now this minus we will send on the side. So within the bracket. So Na is equal to DAB by this Z also we are sending to the bottom. So DAB by RTZ. So we are interchanging the minus. So PA minus PA star. In place of minus, we are interchanging the variable PA minus PA star. This one. So after that, this one DAB by RTZ within the circle term is nothing but a mass transfer coefficient, because for the flux is directly proportional to the driving force, whether it may be a concentration driving force, whether it may be a pressure driving force. Whatever the terms already left apart from the flux and driving force, whatever the terms left is nothing but a mass transfer coefficient. Since this is for gas phase, we can write this is KOG. Overall concentrations we are writing, this is KOG. So we can write as Na is equal to KOG into PA minus PA star. PA minus PA star. We can consider this as equation 2. First one KOL as equation 1 we can consider. This one is equation 1. Okay, now this is overall mass transfer coefficients. Now for the individual mass transfer coefficients, what we can say now for the concentrations we are taking from initial to the final. So this is for overall. So individually when we are taking, see for the gas film, within this film we have to vary the mass transfer coefficient. We have to find out the variation of mass transfer coefficient. So the concentration term is pressure term is varying within the gas phase from PA to PAI. Okay, after this interface the liquid phase will start. Okay, within this up to this interface only the gas phase will be there. So we have to write a same equation for the gas phase, and next one for the liquid phase from CAI to CA it is varying. Okay, up to this interface from this from the right side to the up to the interface it is a liquid phase entirely. So from the left side to the up to interface it is gas phase. So for the individual mass transfer coefficient in terms of gas, this phase we have to use, this region you have to use. For the individual mass transfer coefficient for the liquid phase we have to use this region. So we have to perform first gas phase. So let's see how to perform for the gas phase. Same Na is equal to Ja. See, Na is equal to minus DAB dou Ca by dou Z. Okay. So dou Ca by dou Z. So Na dou Z is equal to minus dAb dou Ca. So now we have to fix the limits. Now we have to we are deriving for the individual mass transfer coefficients. So see, if we are deriving for the liquid, we have to use this region only. So see here Z is equal to 0 means this concentration, CAI concentration. Z is equal to some Z means Ca concentration. Up to these concentrations only we will consider. The limits of Z are yeah. Now the limits of Z are when Z is equal to 0, the concentration is CAI. When Z is equal to some Z, the concentration is Ca. So now derivative integral we can cancel out, derivative integral we can cancel out, upper limit minus lower limit Z minus 0 and upper limit Ca minus Cai. So we can substitute that, we can integrate that and substitute the variables. Na Z is equal to dAb. So dAb upper limit minus lower limit is minus dAb is there. So upper limit is Ca minus Cai. So Ca minus Cai is the upper limit. So in place of this minus, we will set yeah, okay. So we are sending minus to that side and Z to the RHS side. So we will write yeah, we can write Na is equal to dAb by Z, and in place of minus we can write concentration change, we can change variable Ca to Cai minus Ca. Now this we can say dAb by Z is nothing but mass transfer coefficient. Because of these concentrations we are writing for the single phase concentration, so we can take this as KL, which is individual mass transfer coefficients. Yeah, for the individual mass transfer coefficient, single phase we are taking. So we are writing individual mass transfer coefficient KL into CAI minus CA. CAI minus CA. This you can take this equation 3, not now. Just instead of this, we can apply Okay, now uh, just 1 by KL we can write, just sending to this side, KL we have sending to this side, so we can write it as CAI minus CA by NA, this one. So NA, you can take this as equation 3. Then next one, similarly for the gas phase, we already know Na is equal to, for all fluxes, Na is equal to minus DAB dou Ca by dou Z. Instead of Ca, we are substituting for the gases Pa by RT by dou Z. So Na is equal to minus DAB. So RT is not at all variable, so we can separate it from the derivative. So we can write dou Pa by dou Z. So similarly, we can separate the variables Na within the limits dou Z is equal to minus DAB by RT. So within the limits dou Pa. So we are writing now for the individual gas phase. We have to see these concentration. For the single phase we are writing. So Pa, when Z is equal to 0, the concentration is Pa. When Z is equal to some Z, the concentration is PAI. So same thing we have to apply here. When Z is equal to 0, the concentration is Pa. Okay, when Z is equal to some Z, the concentration is some PAI. So now it is also simple integral. So integral derivative cancel. Upper limit is 0, Z minus 0, lower limit is 0. So Z it is. So PAI minus PA is upper limit minus lower limit. So we can substitute Na into Z is equal to minus DAB by RT. So upper limit is PAI minus lower limit is PA. So in place of this minus, we are substituting, we are sending it out. So we are interchanging variable. So this is Na is equal to RTZ, we can write here RTZ into, so in place of minus we can interchange the limits PA minus, now this is PAI. Now this is, now flux is directly proportional to concentration gradient. So whatever the terms other than the flux and concentration gradient left is nothing but mass transfer coefficient. Since this is a gas phase, it is gas phase constant mass transfer coefficient. Since this is, we are writing for single phase, now this is individual mass transfer coefficient. So now this is Na is equal to individual mass transfer coefficient in gas phase into so Pa minus PAI, Pa minus PAI. So now 1 by kg we can write from this equation. So now we can send kg to the LHS side. This is n by kg is equal to Pa minus PAI by Na. So this is equation number 4 we can write. So now using equation number 1. So from equation 1. So equation 1 is this one. This is equation number 1. So equation number 1 is Na is equal to KOL into Ca star minus Ca. Na is equal to KOL into Ca star minus Ca. So from this one we can write 1 by KOL is equal to Ca star minus Ca by Na. So from this one, same equation. So within the RHS side, we have to just add CAI interface concentration and subtract CAI interface concentration. Ca star minus Ca plus CAI once we have to add and once we have to subtract. CAI plus CAI minus CAI by Na is already left out now. Now we have to divide this this overall quantity into two terminologies. So 1 by KOL is equal to Ca star, this minus CAI as one term, Ca star minus CAI by Na as a one term, plus the left out term is CA minus CAI minus CA. This is CAI minus Ca by Na. Okay, already for Ca star, this we already know. Okay, from previous equation number 4 is. Equation number 3. See, from the equation number 3, CAI minus Ca by Na is this one, 1 by Kl. So CAI minus Ca. CAI, this one. CAI minus Ca by Na we can write 1 by Kl. Okay. So 1 by KOL is equal to Ca star minus CAI, Ca star minus CAI by Na, plus instead of that whole quantity we can write just simply individual mass transfer coefficient 1 by KL from equation number 3. Now see, for the concentrations, Ca star, the equilibrium concentration in terms of partial pressures are, when Ca star is there, we can write this as Pa is equal to, from Henry's law, we can write Pa is equal to H into Ca star. So okay, here also the Pa star is equal to Ca, we can write H into Ca, we can write. From the Henry's law, we can write PAI is equal to H into CAI. Nothing but equilibrium concentration expressions. So here if you see, with just 5 minutes I will just complete. Just bear with me. This one, instead of this Ca star, we can write H into Pa star. Pa is equal to H into Ca star. Okay. For CAI we can write PAI is equal to H into CAI we can write. So these variables we need to substitute in place of this one. In place of CAI we can substitute this one. In place of that one we can substitute that one. So in place of Ca star we will substitute. So this is 1 by KOL is equal to, in place of Ca star we will substitute Pa by H minus CAI by H. PAI by H. PAI by H we can substitute. Already Na is there, plus left out term 1 by KL is there. So we can take H as outside. When we take H outside, 1 by KOL is equal to 1 by H we can take outside, PA minus PAI. PA minus PAI by Na. Already this we already know that one. What is Pa minus PAI? PAI minus PAI from equation 4. From this one, we already know PA minus PAI by NA is nothing but 1 by kg. One by KOL is equal to 1 by HKG plus 1 by KL we can write. Yeah, this one in place of that one we can write 1 by HKG. So 1 by KOL is equal to 1 by HKG we can write plus 1 by K. So this is the overall relationship between overall mass transfer coefficient in liquid phase to the individual mass transfer coefficient in the two phases. Similarly, same formulas we can apply to the gas phase also. Gas phase also same formulas we can apply and deduce the other equation. Okay, but first go through the notes. Then if you don't understand, then also I will once again explain this. Yeah, okay. I think I can conclude this one. Okay, you just derive from the notebook, and then if you don't understand, I will just explain once again in the next class. Okay, then we will meet in the next hour. Thank you.